Hi, this is Roger. I am geologist, and here I am telling you the second chapter of my trilogy. It's about the Cenerian Orogeny. The details and the results of my studies can be looked up in the three papers I published in 15, 17, and 2020. What is the reason why I defined the Cenerian Orogeny? Now here in this figure, you see four orogenies which are visualized in a diagram. On its vertical is a time axis, and along the horizontal axis are three different types of orogens, namely the Alpine collision type, then the Andean continental arc type, and the Alaskan type, which are operating by the cratonization of subduction-accretion complexes, as I explained in my first YouTube video. The third information is the paleolatitude where these events occurred on the globe at those times. Now, the reason I named the Ordovician events in the Alpine region and in other parts of southern Europe by the name Cenerian was because we didn't have a name before. And that has led to the strange situation that we have a major crust forming event in the Ordovician, but we don't have a name for it. And therefore, different authors applied different names, like the Variscan. So they spoke about the Variscan event, which reached far back into the Ordovician. But this was not appropriate because the Ordovician events I'm speaking about, they have nothing to do with the formation of Pangaea. The Ordovician events we are talking about are crust-forming events at the periphery of Gondwana. So therefore also the application of the term Caledonian is very misleading, because Caledonian is the collisional event between Laurentia and Baltica after the Iapetus Ocean was closed, and this was far away from Gondwana at another paleolatitude at younger times by another type of orogeny. Other authors applied the term Pan-African or Cadomian to the Ordovician events, but also this is not appropriate because the Cadomian lasted until maybe 500 million years, but not younger than 500 million years. So therefore I decided to give the Ordovician events in the Alpine region and other regions in southern Europe an own name, so we can name and speak with an appropriate term about these events. Also to distinguish these events from other events, like shown here. This figure is an attempt to show the generation and evolution of the southern European crust in a tree plot. So we have a triangle, and at each corner is a specific type of orogeny. So we have the Andean type orogeny, which is subduction related arc, which probably was the setting in Cadomian times, so in Neoproterozoic and Cambrian times. And the oldest rocks in southern Europe were generated during the Cadomian, which is a kind of peripheral Pan-African belts. Now, as we follow the gray arrow, which is a a path through times, and the numbers in these boxes are the ages in million years. So as we come into the Ordovician, we probably increased the sediment input from the eroding Pan-African belts. We increased the sediment input in a circum-Gondwanan subduction system, and by that we developed these cratonizing subduction-accretion complexes. And one of them was the Cenerian belt, which was located north of Gondwana. And these Cenerian Orogeny recycled Pan-African detritus and formed large parts, or the main parts, of the South European crust during Ordovician times. Later, in the middle to late Paleozoic, we had the major collision during the Variscan event, where we formed Pangaea, and then today we have the Alpine collision. But the Alpine collision was not a crust-forming event, because there we had already formed crust which collided passively, you can say. But the crust-forming events were back in Variscan, mainly during the Cenerian and the Cadomian events. This is a flow diagram with a time scale beginning at about 1 billion years, reaching to today. And it shows the assembly of supercontinents and their splitting. And the splitting is symbolized by blue arrows. And in between the smaller continents, we have the formation of oceanic basins. And on the contrary, the red arrows, they symbolize collisional events where we form mountain belts. Orogenies at the periphery of continents related to subduction or subduction-accretion are written in italic letters, like here, for example, the today's Cordillera Belt at the rim of America. And if they're underlined, we have the formation of subduction-accretion complexes like in the Paleozoic, the Lachlan Fault Belt in Australia, or during the Ordovician, the Cenerian belt. Now we can make, in this flow diagram, we can make time shots at defined times, like for example in the Ordovician here. And then we see that in the Ordovician we have no collisional events. We had subduction-related magmatic arcs, or when sediment input was high, we have the formation of subduction-accretionary complexes, like the Lachlan Fault Belt and the Cenerian belt here north of the Gondwana supercontinent. With this slide, I'd like to refer to the paper of Reno et al. 2008, which was for me a very important paper, because these authors, they analyzed the circun ages of river sediments from all over the world, and as they stacked the results on top of each other, they see in this cumulative curve at what time in the Earth's history, from the beginning to today, we had the most intense crust-forming events. And these events, they relate to the formation of supercontinents. And what was important for me is to see that the formation of Gondwana was, you can say, one of the major crust-forming events in the Earth's history. And the erosion of these Pan-African belts, that's where in the Ordovician we grow Gondwana at its periphery by the formation of cratonizing subduction-accretion complexes. And This information, combined with the reconstruction of a Gondwana subduction system by the same authors, that inspired me a lot in the development of the concept for the Cenerian Orogeny. With this slide, I want to address the topic Gobe, and this was not topic of my research, so there are other researchers which dedicated their resources to this phenomena called the Great Ordovician Biodiversification Event. And what that means is that along the time scale here, we have the Cambrian explosion of life, where we formed, or where the major basic types of animals were formed. And this explosion actually had a continuation during Ordovician times. This is the Ordovician period here, where the number of families or the number of type of fossils exploded further. And the reason I mention this is because not only myself, but also others think that there's a relation between Gobe and the formation of subduction-accretion complexes. Because the generation of subduction-accretion complexes needs a high sediment input, and this is probably in favor for the plankton because they have a lot of nutritions to evolve themselves and to grow in number and species. And the other aspect is subduction-accretion complexes generate shallow marine environments. And as these breeding places grew in number and size on a global scale, this was probably one of the preconditions to let Gobe occur in Ordovician times. This map I have already shown in my first video, and it is a reconstruction based on the works of other geologists. And it shows the situation at the beginning of the Paleozoic era. So it was actually when the Cadomian arc was active, where parts of the Terra Australis origin were active. And later on in the Ordovician, the Cenerian Orogeny became active in this region, where then the southern European crust was formed. Therefore, the term Cenerian is kept in brackets because it's a little bit later according to this reconstruction. And also the Lachland fault belt was occurring in Ordovician and Silurian and Devonian times, so a little bit later. What is interesting to compare the Lachland fault belt with the Cenerian fault belt is that the Lachland fault belt is, as far as I know, the only location on Earth where this peripheral situation at the rim of Gondwana was conserved. So there was no later collision like here. Later on, we had the Variscan event with the formation of Pangaea, and this was in the middle of Pangaea. So it was totally crushed, and later on we had the Alpine collision, again crushing on top of these regions. But here in the Lachland fault belt, we have the original configuration when the Lachland fault belt was generated still there, and we can actually study there a fossil situation, how it might have looked in northern parts, north of Gondwana, before the Variscan event occurred. That was actually the reason why I went to Australia to study the Lachland fault belt and to compare the Lachland granitates with the Ordovician orognesis of the Southern Alps. This is an unpublished compilation of different tectonic models you can find in the literature. The reason I made this compilation is because literature is very confusing. So the different papers which are listed here, and these are the topics or the regions they are referring to, you can group them into 9 models, and these 9 models you can subdivide into 3 categories. So these models here, they try to explain this perluminous magmatism in a back arc environment, where they also try to explain the accumulation of these large amounts of gray wackies. Another group tries to explain these accretion origins by the accretion of terranes, of foreign units being attached to a rim. And these models here, they work with the accretion of gray wackies. This model here with the red frame is the model I developed to explain the generation of the continental crust in southern Europe. What is different to other models, or to many of the other models, is that I don't have a different lower crust. Like, for example, here they operate with a thin old continental crust, and on top of that you have the accreted gray wackies. So I come up with a model with an accretionary complex which is fully composed of gray wackies, which are going to melt in their lowermost part, and from where you generate and intrude the perluminous magmas. This is also an unpublished figure where I tried to apply the model of cratonizing subduction-accretion complexes, which was originally developed by Keith Crook in 1980 for the Lachlan Fault Belt, to reapply it to the Lachlan Fault Belt. And a main assumption and justification for this application is that I say the reason why these cratonizing subduction accretion complexes are not creating thick mountain belts which are going to be eroded, and then you expose the middle crust and lower crust to the surface. So you in situ cratonizing these accretionary complexes. That means that the lower crust stays in the lower crust, the middle crust stays in the middle crust, and the upper crust stays where it is. Therefore, the Lachlan Fault Belt, which never experienced a younger collision, which turned the original configuration upside down, like in the southern European region, where we had the Variscan collision. In the Lachlan Fault Belt, we therefore only see the upper crust, and the geologists don't know what's in the lower crust. On the other hand, in the pre-alpine polycrystalline basement units, due to the younger collisions of the Variscan and the alpine orogenies, we have exposed the Ordovician lower crust. And we know how the lower crust looks like. So therefore, that is my main assumption, I say what we see in the alpine region, what happened in the Ordovician, relates to what we see in the Lachlan Fault Belt in the upper crust. And thinking these two regions together allows you to develop a model through the entire crust. And therefore also I think that applying the model of cratonizing subduction accretion complex to the Lachlan Fault Belt makes things much easier. The only thing you have to incorporate is that you have to double the situation in order to explain the different arcs which finally collide to assemble the Lachlan Fold Belt. But I don't want to go into details at this stage, just to show you that there's a great potential of these models to apply them to other regions with a similar geology. These are the four profiles which are also on the previous slide. They're a little bit enlarged so that we see how the Lachlan Fold Belt might have been developed during these different times. And as I said before, we have the complication of a large transform structure which allows us to double actually the scenario, and at the same time we can explain that these greywacke as well as these greywacke were derived from the same Australian craton. We can also explain how the magmatic arcs were generated as a function of the subductions which generated these primary basalts, which then intruded at the base the accreted greywacke, and as a result of that we developed a perluminous magmatism at different ages. A special feature of the Lachlan Fold Belt is the IS line. That's a line dividing a region where we have predominantly S-type sedimentary derived granitoids versus regions where we have both sedimentary derived and so-called igneous derived granitoids. But I come to this later, actually in the third chapter of my trilogy. So that means in the next YouTube movie. I come back to the Cenerian orogeny. The name Cenerian comes from the Ceneric gneiss. And the Ceneric gneiss is a very special orthogneiss from the Strona-Ceneri zone in the southern Alps, which generated by the melting of greywacke. And Ceneric gneisses are very typical for cratonized subduction-accretion complexes, where, like here shown, we have the melting of greywacke at the base of such accretionary complexes. And these melts start to being dislocated, probably along steeply plunging shear zones. And then we develop, from these migmas, we develop diatexites and S-type granitoids. Such generic gneiss, like lithologies, they have a paragneiss composition, so they have compositions like greywacke, but they have granitic structures. And actually the Kuma granodiorite, which is the type locality of Chappell and White's S-type granite, which is, by the way, also located here, these are key lithologies indicating this particular setting of subduction-accretion complexes which cratonize during periluminous magmatism. And periluminous magmatism means melting of greywacke. So what I did here is I tried to allocate the different pre-alpine crystalline basements according to their pressure indicators in the corresponding depth of the crust. And I did something similar for granitoids in the Lachlan Fold Belt, and that's the Lachlan Fold Belt, as there are only the shallow crust levels exposed, we don't have information from deeper parts. And that's what I mentioned earlier, makes it interesting to compare the two regions. Because here we gain information from the deeper crust, and we can compare that to what happened in a similar setting in the upper crust. So the concept of generating magmas by anastasis is an important concept to understand these subduction-accretion complexes with perluminous magmatism. Yeah, to give you an image of the generic gneiss, I take here these photographs out of my PhD thesis. Here you see two figures, figure A and C, from the generic gneiss, and on the right you see very similar pictures from the Cooma granodiorite of the Lachlan Fault Belt in Australia. So we have a granitic texture, and here we have a discordant and intrusive contact. Here, this is a xenolith, a meta-greywacke with an older bedding, older schistosity. It's a very sharp contact. And sometimes these inclusions are very edgy, very angular. Sometimes they're very roundish, and sometimes they're hardly to recognize anymore because they're already assimilated to a degree where we can say these are ghost-like xenoliths. So this shows that we have different grades of assimilation. And these are exactly the same observations you can make on the other side of the globe. Again here, this is a compilation of pictures. On the left, we have macroscopic observations of the generic gneiss. We have these meta-greywacke inclusions. In the core, we have calc silicate nodules. And here we have quartz lumps. So this is another quartz lump, which do not melt, so they resist melting. And this is also described for S-type granitoids in the Lachlan Fault Belt. We have these resistors. So we have meta-greywackes which do not melt at the rim of calc-silicate nodules. And we have these quartz nodules. And quartz nodules, that's very typical for S-type granitoids. These might be old quartz from veins from the protolith. And when the greywackes with the quartz veins are going to melt, these pure quartz veins, they resist melting and they survive as quartz lumps. So these type of S-type granitoids are very rich in inclusions. And on the other side, if the xenoliths are going to melt, very often we have restites very rich in biotite. That's another feature of these special S-type granitoids. I like to conclude with my first slide of this second chapter of my trilogy about the Cenerian Orogeny. So we have seen that the Cenerian Orogeny is an Ordovician crust-forming event in southern Europe. It operated by the formation of cratonizing subduction-accretion complexes. And during the cratonization, we had based perluminous magmatism, which generated these orthogneises. And this model for the Cenerian orogeny could also be applied to other circum-Gondwanan regions in the early Paleozoic, nevertheless, probably also to the Lachlan Fault Belt. And if you are interested in further details, I again refer to my papers where you can get much more information about the Ordovician Orogeny in the Alps, then about the Cenerian Orogeny, what are the detailed arguments for that event, and to justify a specific name for it. And in my next and last chapter, I will refer to banded amphibolite formations and how these special rocks are related to perluminous magmatism. Thank you for your interest.